g of a is a multiple of p squared for really mod p reasons. In that if you change a by something mod p, it continues to remain a multiple of p squared. So if g of a prime is congruent to 0 mod p squared for all a prime congruent to a mod p, then we say g of a is strongly a multiple of p squared. Okay, it's really strongly a multiple of p squared because if you just replace a by any translate by a multiple of p, it continues to remain a multiple of p squared. Okay, so that could happen. If it doesn't happen, we say it's weakly a multiple of p squared. So in other words, that g of a is a multiple of p squared, but you can change a by some multiple of p so that it's not a multiple of p squared anymore. So in that case, it was kind of more weakly a multiple of p squared. Instead of strongly or weakly, I like the terminology. So in the first case, g of a is a multiple of p squared for mod p reasons. Okay, you translate a by something mod p, and it continues to stay a multiple of p squared. Whereas in the second case, g of a is really a multiple of p squared for mod p squared reasons. That the residue of a mod p squared really matters in making g a multiple of p squared. So these are two distinct things that can happen when g is a multiple of p squared at a. Is that clear? Any questions about that? So just to give you an example, if you take the two-variable polynomial f of x comma y equals x times y, then you can see both cases happening, right? So if you look at x times y, it can be a multiple of p squared for mod p reasons, namely when both x and y are multiples of p, right? Then if you change x and y by any multiples of p, it will continue. X times y will continue to be a multiple of p squared. So that's a case where x times y is a multiple of p squared and y is relatively prime to p. And that's the case where x, y is a multiple of p squared really for mod p squared reasons. Because if we changed x by just p, that wouldn't be true anymore, that x times y is a multiple of p squared. And so one elementary but key observation is that it's natural to try and estimate how often each of these two different kinds of becoming a multiple of p squared happen. And so that's what we're going to do. We're going to look at those two cases separately. Okay, so the point is that the case of strong multiples, in other words, multiples of p squared for mod p reasons, can actually be handled totally generally for an arbitrary multivariable polynomial. That's what I want to show you first. So it turns out strong multiples of p squared, in other words, multiples of p squared for mod p reasons, can be handled by algebra and geometric techniques. And for an arbitrary polynomial, we're not even talking about the discriminant polynomial yet. So the observation is that we can actually handle for any polynomial and at least two variables. Okay, so to estimate strong multiples of p squared, we use the following theorem, which a lot of us are now calling the Ekadal sieve, but this is based on a quantitative version of the Ekadal sieve. And the statement as follows. So suppose you have some subvariety of n-dimensional space defined over Z with codimension at least 1. In other words, you have some subscheme of an over Z with codimension at least 1. And suppose you want to count. Okay, so we want to count the number of integer points, number of lattice points, a and z to the n, okay, of bounded height. So in other words, all the coordinates are at most x in absolute value, such that if you reduce a mod p for some large p, you end up on that variety, the reduction of that variety mod p. Okay, so all lattice points in a big ball, such that when you reduce them mod p for some large p, you end up on the variety mod p. Okay, how many such points are there? The trivial estimate is x to the n, right? So if all the coordinates are bounded by x, okay, their total number of such points is x to the n, but we want a saving over that. So we want to say that not all x to the n points have the property that when you reduce them mod p for some large p, you end up on the variety mod p. So this m you want to think of as just being sort of a small power of x. So in all these kinds of sieves, you want to understand p squared dividing your number for some small power of the height, and show that that doesn't happen too often. So this is kind of a statement of that form. So here's the saving that we get. So it's not all x to the n points will reduce mod p to a point on the variety mod p. So if k is 1, this is not saying anything. So this really kicks in when k is at least 2. If the variety is at least codimension 2, then we're saying that not all such points have that property. We get a saving of m to the k minus 1 here. And then this is also less than, the second term is also less than x to the n. So this is strictly less than x to the n, smaller order, when m is a small power of x, and k is at least 2, the codimension of your variety is at least 2. And this is exactly the kind of estimate that we'd like for p squared dividing g of a. But instead we're asking for, so instead of asking for p squared dividing g of a, we're asking for a mod p to lie on some codimension variety, codimension 2 variety over z, reduced mod p. Okay, any questions about the statement of that? And I'll explain why it's relevant to the square free problem. But this is just a general, method that works when you have such a situation when you're interested in the reduction of points mod p lying on a fixed variety over z mod p. And here the implied constant depends only on v. So let me explain why this is true. For k equals 2 is where we're going to use it, so I'll just give you the sketch of the proof when k equals 2. Okay, so let's suppose that this subvariety of an of codimension 2 is just given, without loss to generality, you can assume that it's just given by the vanishing of two polynomials, say g and h. Say it's given by two integral polynomials, g and h, equals 0. Okay, and we want to count how many points there can be such that for some prime p bigger than m, when you reduce it on p, you end up on the variety. Well, what we do is, let's fix the first n minus 1 variables. Each of them is going to be at most big X in absolute value. So there are x to the n minus 1 possibilities for those first n minus 1 variables. Okay. And then we want to say what can happen to that last variable. And we're going to find that it's restricted. Okay, and the reason is, so once you fix the first n minus 1 variables, see, I assumed one thing about the two polynomials, which is the first polynomial is not involving x dash. We can assume that if your codimension 2 variety is given by g equals h equals 0, by elimination theory, we can get rid of the last variable in the first polynomial, say g. So we can assume g is just a polynomial in x1 through xn minus 1, whereas h involves all the variables. Okay, so that you can do by elimination theory. For example, replacing g by the resultant of g h. So now if you fix the first n minus 1 variables, then the value of g is determined. So then g of x1 through xn minus 1, well, it's determined once you fix the first n minus 1 variables, and it can only have boundedly many prime factors p bigger than m. Because p, remember, we assume is a small power of x. So once it's at least a small power of x, then there can only be boundedly many prime factors that are bigger than m. And so that essentially determined p. Right, just by fixing the first n minus 1 variables, p is determined up to boundedly many possibilities. Let's take any one of those boundedly many possibilities for p. So for each such prime p, we now need to solve h of x1 through xn is 0 mod p, which is just a polynomial equation in one variable, which has a bounded number of roots mod p. So that means that the total number of possible x1 through xn is, well, x to the n minus 1, which is the total number of possibilities for the first n minus 1 variables. And then remember, that fixed the prime, and now h of x1 through xn has to be 0 mod p. That fixes boundedly many possibilities for xn mod p. And for given xn mod p, how many integers between 0 and x can be a given value mod p? Well, the answer is x over p, okay, which is bounded below by x over m, okay, and bounded above by x over m. Plus 1, you always have to add that plus 1, because even if your range is small, you may still get one root in there. So total number of possibility for x1 through xn is O of x to the n minus 1 times x over m plus 1. That's the upper bound for how many possibilities there can be. for x1 through xn. And that's exactly O of x to the n over m plus x to the n minus 1. So that's exactly the bound we wanted when k is 2. That's how we prove the result when k is 2. So that gives a saving. Even if k equals 2, this is strictly less than, smaller order than x to the n. It's a non-trivial saving. Yeah, right. So actually, yeah, I skipped lots of cases that, yeah, so one couldn't quite do this. One couldn't say G has only boundedly many prime factors if G turned out to be 0. So you have to handle that case separately, right? The number of places where G is 0 is also on the order of x to the n minus 1, you have to show. And there are many little cases like that arise on the way, but that's right. Any other questions? Yeah. That's right. If the polynomials vanished identically, yeah. Right. So H, it's possible that H also vanished at that choice of x1 through xn minus 1. So you have to count how many x1 through xn is 1 would that happen to. So those are the little subcases that you sort of have to analyze. But the basic idea is that for most things, G is not going to be 0. That will determine the prime. And then when the prime is determined, H will not be 0. And then that will determine xn to bounded limit mod p. Okay, so the point is that if you're counting points that reduce mod p to something on a codimension 2 variety over z mod p for some large prime p bigger than m, then you do have non-trivial saving. And so how do we handle strong multiples of p squared? Well, we observe that if g of a1 through an is a multiple of p squared for mod p reasons, then if it's for mod p reasons, then if you think about it, both g and its partial with respect to, say, the last variable will have to vanish mod p. And so if g is becoming a multiple of p squared for mod p reasons, if it's mod p reasons, there has to be something codimension 2 mod p going on, for just mod p reasons implying being a multiple of p squared. And in fact, explicitly, both g and its partial have to vanish mod p at that point if g is a multiple p squared for mod p reasons. So you can think about that just by, say, fixing the first n minus 1 variables and just thinking about it as a polynomial in the last variable. You'll see that right away. Say by taking the Taylor expansion with respect to the last variable. You see it that way. So, in other words, a1 through an will lie on a fixed codimension 2 variety, mod p. That fixed variety being the variety defined by g and its partial with respect to the last variable. And so we can use the Ekadel type estimate from the previous page to get the saving that we wanted. So what we'd get is that the number of points in a big box of side length x that are multiple, where g takes a multiple of p squared value for some p bigger than m is a strict power saving. It's a strict saving over the total x to the n points. And that's exactly what you need to do, is square free save, at least for those points where p squared divides g for mod p reasons. So strong multiples can actually be handled totally generally for any polynomial in at least 2 variables. So this argument holds for any multivariable integer polynomial. Nothing special about polynomial strings. And that's been very useful for us in handling other polynomials as well. We know that we can dispose of this case right away for any polynomial in at least 2 variables. So it therefore remains to estimate the number of weak multiples of p squared. In other words, places where f is a multiple of p squared genuinely for mod p squared reasons. And if you look at all the literature in it hasn't been phrased this way, but wherever the difficulties come in square free sieves, this is where they come. It's where things are becoming multiples of p squared really for mod p squared reasons. Okay, so how do we deal with those? In all the polynomials that we've been able to handle, we deal with it as follows. We do some change of variable to transform weak multiples back into strong multiples where the Ekadel sub does apply. So that seems counterintuitive. It's really happening for mod p squared reasons, but often there is a change of variable you can do so that suddenly the weak multiples become strong multiples, and then you can apply that. geometric sieve. Okay, so I want to describe how we do this transformation in the case of polynomial discriminants. So the idea is to embed the space of monic polynomials into a bigger space where there are more symmetries, so there are more transformations around, and where we can do this embedding so that polynomials whose discriminant is a multiple of p squared for mod p squared reasons are mapped into points where suddenly it's changed into mod p reasons. So we're taking our space, we're embedding into another space where the mod p squared reasons have suddenly changed to mod p reasons. And I'll show you explicitly how that happens in this case. Okay, but to do this, we first have to understand, okay, because we have divided into these two cases, the strong multiples and the weak multiples. Before we know what's happening to the weak multiples, we have to know where they are. So we have to understand how a polynomial can have discriminant a multiple of p squared, first of all, and then when it is a multiple of p squared, when it happens for mod p reasons, and when it happens for mod p squared reasons. Okay, so let's talk about the case where the discriminant is a multiple of p squared for mod p reasons. So in other words, you just care about how the polynomial factors mod p, and that tells you that the polynomial discriminant is a multiple of p squared. So how does that happen? So here's the lemma that tells you exactly when a polynomial has discriminant a multiple of p squared for mod p reasons. Okay, so monic integral polynomial has discriminant a multiple of p squared for mod p reasons if and only if, modulo p, it has a root of multiplicity at least 3, right, or at least 2 multiple roots, right, multiplicity at least 2. Right, and that's kind of clear from the definition of the discriminant. So remember, the discriminant is the product of the differences of the roots. So if you're going to get p squared divided by discriminant, you need some roots mod p to be coming together, if it's only happening for mod p reasons. Okay, so these are the kinds of cases with that the discriminant becomes a multiple of p squared for mod p reasons, and these can be handled, as I said, using the Ekadal-Siv method. So we don't have to worry about when p squared divides the discriminant for reasons where roots mod p are coming together multiple times, because that lets you on a codimension 2 variety of geometric sieve. Okay, so now we need to know when can the discriminant become a multiple of p squared for mod p squared reasons. Okay, so there, you're not going to have lots of roots coming together, you're just going to have 2 roots coming together, but they're coming together so much that they're coming together mod p squared. So when is the discriminant multiple of p squared for mod p squared reasons? That's given by this lemma. It says that a monic integral polynomial f of x has discriminant a multiple of p squared for mod p squared reasons, if and only if you can translate the variable, like say k and z, so that f of x plus k has last coefficient of multiple of p squared, and the second to last coefficient of multiple of p. So when you write down your polynomial, the very last coefficient will be multiple of p squared, and the one right before that, coefficient of x, will be multiple of p. So the polynomial ends with a multiple of p and then a multiple of p. And so there you can see that there's only just a double root. It's only a double root. Okay, but because that last coefficient is a multiple of p squared, it causes the discriminant to vanish mod p squared. And you can see explicitly that it's happening for mod p squared reasons. That last coefficient being a multiple of p squared is what's causing the discriminant to become a multiple of p squared. And if you change that p squared to a p, it would only force the discriminant to be a multiple of p. So that's why it's only for mod p squared reasons that the discriminant is being a multiple of p squared in this case. Okay, so those are the weak multiples of p squared. And the question is, how can we lift such polynomials to a bigger space with more symmetries, so that the mod p squared condition changes to a mod p condition. So somehow we want to take that p squared and split it up into 2 p's and cause that to be a codimension 2 condition in your bigger space. Well, a natural thing to do, one way to get p squared for mod p reasons is, if the p squared is arising as a determinant, where there were like two p's on the diagonal, right? And that would break up the p into two p's, and when you take the determinant, it would squash the two p's into a p squared. And so, yeah, that is what we do. So we can actually do it with symmetric matrices. So we show that there exist n by n integer symmetric matrices, A and B, such that if you take determinant of AX minus B, right? So if A and B are n by n matrices, then if you take determinant of AX minus B, that is a polynomial of degree n in X, right? So the determinant will be degree n. So for such an f of X, where the discriminant is becoming a multiple of p squared for mod p squared reasons, we find integer matrices A and B, such that determinant of AX minus B is f of X. Okay, so that's like our list. Our f has been mapped to space AB, and the map is just taking the determinant of AX minus B to get back to the polynomial. And what further properties do these A and B have? Well, if you look at the polynomial delta n of determinant of AX minus B, okay, so if you have two matrices, n by n matrices A and B, there's an actual discriminant polynomial on pairs of matrices A comma B. Namely, you take the discriminant of determinant of AX minus B. So that's a polynomial in the entries of A and B. Right? Its degree is suddenly n times more than it used to be, but it's still a polynomial in the entries of A and B. And we're going to find this lift from f to A comma B, so that even though a discriminant of f was a multiple of p squared for mod p squared reasons, if you look at it now, the discriminant polynomial on A comma B, it's the same value, it's still a multiple of p squared, but it's now happening for mod p reasons. And the way we're going to do that is we're going to take that p squared, which is arising as the determinant of b, and we're going to split the two p's, right? Put them on kind of diagonal. So I'll actually show you what the matrices A and B are. So I'll show you in the case n equals 5, so degree 5 polynomials. So imagine you have a quintic polynomial, monic, f of x, such that the last coefficient is a multiple of p squared, second to last coefficient is a multiple of p, and we're going to lift it to an A comma B. This is going to be our A, so it's just a split quadratic form. And why is this good to take as A? Well, remember we wanted the polynomial to be monic, and the determinant of this is 1, so that's good. So if you take the determinant of AX minus B, automatically this will cause it to be monic. And what do we take for B? We take that thing. And you'll notice how these p's have been split apart here. What is it? So what is the final coefficient of determinant of AX minus B? The last coefficient is determinant of B, right? And what is the determinant of B here? Well, you see that it's just p times c5. So it's c5 times p squared. So it's an arbitrary multiple of p squared if you choose. So c5 is arbitrary. But notice the p's have been split into two there, which is useful for making the n discriminant a multiple of p squared for mod p reasons. So if you work out what the determinant of AX minus B is for these two matrices A and B, you find that first of all it's monic, and then the next three coefficients are totally arbitrary, and then the next coefficient is p times c4, and the last coefficient is p squared times c5. So an arbitrary thing times p, and then an arbitrary p squared times arbitrary thing times p squared. So this is like the totally general form of the polynomial, where the discriminant is becoming a multiple of p squared for mod p squared reasons. But the point is that if you don't view this discriminant polynomial in terms of the coefficients of the quintic, but if you view it as a polynomial in the coefficients, in the entries, non-zero entries that you see of A and B, you check that the discriminant is actually becoming a multiple of p squared now for mod p reasons. If you change all these non-zero entries that you see by just multiples of p, the discriminant of determinant of AX minus B will still remain a multiple of p squared. It's really now happening for mod p reasons. So if we view this discriminant of determinant of AX minus B, which is just the discriminant of f, as a polynomial, not in the coefficients of f, but in those 12 12 variables of B, so we're actually going to always fix A to be that, so that's not even part of the variable. And we're always going to take this top 2 by 2 block of B to be 0. So we're not even going to consider those as variables. So the number of variables that remain is 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12. 12 variables of B, right? That's the things above the main diagonal. Not in that top 2 by 2 block. The 12 variables of B. And if we look at this discriminant as just a polynomial in those 12 variables of B, then it turns out that this discriminant is a multiple of p squared in these 12 coordinates for mod p reasons. This p squared has been split into those p's, and now the discriminant becomes a multiple of p squared for mod p reasons. Even though the discriminant has a polynomial c1 through a1 through a5 was multiple of p squared for mod p squared reasons, but we split apart those p squareds into two p's. Okay, so this looks great. It seems like now we can just apply the Ekadel sieve and we'll be done. No, because something funny happens. So we were very excited when we found this map. Yeah, suddenly mod p squared reasons had been changed to mod p reasons, and this is great. But something funny happened, which is that it is for mod p reasons, but it's still only lying on a codimension 1 variety, not codimension 2. How is that possible? I'll explain that right now. Because it seems like if something's vanishing mod p squared for mod p reasons, it has to lie on a codimension 2 variety. How could it suddenly have only been on a codimension 1 variety? Well, here's why. So, okay, first of all, let me explain what the symmetries are. This space B has 12 coordinates, and as I said, we wanted more symmetries. This space has a lot of symmetries. Let G0 be the subgroup of the orthogonal group of A. Okay, that keeps the top 2 by 2 left corner of B 0. So in other words, SLN acts simultaneously on A and B because they're both quadratic forms, by multiplication on the left and multiplication by transpose on the right. But we don't want to use all of SLN because we want A to remain the split form. So the subgroup of SLN that preserves A is the orthogonal group of A. So if we have the orthogonal group of A act simultaneously on A and B, A will remain as it is because it's the orthogonal group of A, and then B will move around. But now we want to take the subgroup so that it also preserves the top 2 by 2 block. Okay, that's some non-reductive subgroup of SOA, but it's a fairly big group. So that's going to be our group G0. And so G0 is a symmetry of this whole situation, of these kinds of shaped matrices. G0 acts on pairs A comma B, but it preserves A because it's in the orthogonal group of A, and it preserves the shape of B by definition. And of course, note that the action of G0 also preserves equation 1. In other words, determinant of AX minus B will remain that polynomial even when you act by G0, right? Because determinant, so multiply on the left and right by determinant one matrices. It's not going to change the determinant, so it preserves that fact that you're getting that polynomial f of x. So that's what I meant by having symmetries, that we found two matrices that the determinant of AX minus B is f of x, so we can act on A, B by this huge group and still get lots of other matrices. One can work out what the invariants are for this group action. The invariants for the action of G0 on this 12-dimensional representation V, well, there are 5 invariants that you see right away. C1, C2, C3, C4, C5. Those remain invariant. But if you do a dimension count, you find that that's not everything. There's one more invariant that's lurking around. So when G0 acts on this 12-dimensional representation, you do get the coefficients of f of x, but you get one other invariant. So together with one additional invariant, which we call the Q invariant. And the Q invariant, it turns out, just involves these top 6 entries of B right here. And that there's one invariant defined polynomial in these 6 entries right on top of B there that remain invariant under this action of G0. There's that one invariant, degree 6 in this case. And so you might wonder, what does that invariant evaluate to? Well, so our first 5 invariants were C1, C2, C3, C4, and C5. There's one thing in the picture that we did use. If we evaluate Q on these pair of matrices A and B, we find that Q of AB equals P. So we've embedded the space of monic polynomials into a bigger space where with more symmetry, such that the space of invariants are the coefficients together with this p, has come out as an extra invariant. So what that means is that we have this invariant polynomial q of ab, and we know that p squared divides the discriminant. In general, what happens here, as polynomial, q of ab squared divides the discriminant of a comma b. So even though the discriminant on monic polynomials is an irreducible polynomial, when we've done this lift to the space ab, it's actually become a reducible